So, welcome back. So, for those of you who have noticed that myself and Shivaji shared a similar looking shirts, that's a good observation. We did not plan it, but yes. Yeah, we will start right now. This is a different equation altogether now. So far we were studying this first order differential equations. Today I will start this equation known as the wave equation. Okay? So, wave equation is this equation which you see here. Okay? Again, this is a partial differential equation, so you need to have at least two independent variables. So we take these two independent variables t and x, where x runs in R and t also runs in R. Okay? And this is a second order partial differential equation because you have got second order derivatives in the equation. Okay? So you are looking for a function u such that if you differentiate twice in the t variable and you differentiate twice in the x variable, those two things should match at every point x and t. Okay, x comma t. So then if that happens at every point x comma t in R cross R, you call that function u as solution to the wave equation. Okay? So this is our starting point. We are trying to understand solutions to this equation. Okay? So let us make some very useful observations about this particular equation. Can you click on that again? On the screen, anywhere. Yeah, thanks. So let's make this first observation. So you take a function u which solves the wave equation. Okay? So somebody gives you that function u and let's just keep that as our reference. Then you take any two numbers a and b, real numbers, and you define this new function v. What are we doing when we are defining this new function v? You are essentially translating that function u. Okay? See, the value of v at a point x comma t is essentially the value of your solution u at a point x minus a, t minus b. You are essentially translating the points, okay, by a given vector a, b. So that's what a and b are fixed here, and you do this. The first observation is, and u is that function which solves this wave equation. Okay. The first observation is this translate of u also solves the wave equation. So it's essentially a copy of u, but translated. Okay. V also solves the wave equation, and this you can verify. You see, for any function to satisfy the wave equation, what we need to do? We need to differentiate twice with respect to t. We need to separately differentiate twice with respect to x, and make sure that at every point those two things are the same. And that's what happens when you differentiate v with respect to x and v with respect to t. Because these a and b are fixed numbers, it does not see the differentiation. Okay, and u is satisfying the wave equation everywhere in R cross R. So v will also satisfy the wave equation everywhere in R cross R. This is the first observation. And the fancy way to say this is the wave equation is translation invariant. Okay, so by that they mean this. You translate your solution by a given vector, you are actually getting a new function which is essentially the copy of that original function. Okay. The next observation is, suppose somebody gives you a solution to this problem, the wave equation u, and I blindly differentiate it. Suppose it's a smooth function, you can differentiate it how many times you like, and here I have simply differentiated that function alpha times in t variable and beta times in the x variable. It turns out that this is a new function altogether now, a function of x and t variables. That fellow also solves the wave equation. See, as long as this slide is concerned, we are only worried about satisfying a particular equation. Okay? So, as long as this differentiation is allowed, that means your u is a smooth function, that derivatives of your solution also solve the wave equation. Okay? And this is another very important property about the wave equation. Suppose you give me two functions, u and v, will solve the wave equation. Okay? Then I simply take a linear combination of them. I multiply by some constant alpha to u and another constant beta to v, and I add them. I get a new function, and that fellow also solves the wave equation. Okay? So, this is known as the superposition principle. Okay? These are just names I am throwing, but this is what it means. You give me two solutions, you add them, take the linear combination, it also solves the wave equation. Okay? And this is all possible thanks to the linearity of the equation, but don't worry about that. Okay, so these are the certain properties that we keep in mind. These all could be some of the problems in the problem sheet. You can try. I mean, these are just straightforward. See, you are given some function, you have to show that it solves the wave equation. What do? You differentiate this function twice in t, twice in x, and show that they are one and the same. It will come in handy that u and v are themselves solutions to the wave equations in order to show that. Okay? See, there is no data here. We are just worried about solving a given differential equation. Okay? Any function which solves this at every point x comma t in r plus r, we say it solves the wave equation. Next, this is another very useful property of the wave equation. Again, you take a solution u which solves the wave equation, and you pick some scalar a which is non-zero. You pick some number which is a non-zero real number, and you define this new function v. Unlike the way we did the translation, you see, we took those two numbers a and b, we wrote u evaluated x minus a and t minus b. Here we are doing slightly different. We are evaluating u at alpha times x and a times x and a times t. That's the new point where you evaluate. Whatever evaluation you get, you assign it for the value of v at x comma t. Okay? This way you define this new function v. And it turns out that this new function v also solves the wave equation. Provided u solves the wave equation, v also solves the wave equation. And this is just an easy consequence of composition rule for differentiation, because every time you differentiate u, okay, every time you differentiate v with respect to x, you are differentiating u with respect to the first variable, and then you have to differentiate that variable also. That's just chain rule. You get an alpha or a, okay, and you have to differentiate twice anyway, you get a square. When you do the same thing in the t variable, you get another a square. So you can just factor a square out and use the fact that u solves the wave equation. I request you all to try this computation. Okay, this is a very useful property for the solutions to the wave equation, that this is known as the scale invariance which is present in the wave equation. Okay, that if you scale both the variables in the exactly same manner, you are scaling x as alpha x, ax, and t as at, that happens. There's a similar scale invariance involved in the heat equation, and that I will comment on later. Okay, you have to slightly change the scaling when it comes to the heat equation. So this is one thing. So v also solves the wave equation. Now this is another useful property, and this kind of hints at its relation to the transport equation that we have studied. You remember the very first equation that we studied, the transport equation, we said that, okay, any function of x minus y is a solution to the transport equation. And somehow a similar property holds for the wave equation also. You give me any smooth function f, and you evaluate at x minus t, and that is the assignment that you give for this function v. You define a new function v of two variables such that v at x comma t is essentially this given function f at x minus t. F is just a function of one variable, so you have to input only one variable there. So you can check that if f is a smooth function, by that we mean if you are allowed to differentiate it twice, you can show that v also solves the wave equation. For any smooth function f, v solves the wave equation. Okay? Because this is what is happening here is, once you differentiate f with respect to x, you keep getting f double prime evaluated at this. But when you differentiate this with respect to time, you get f double prime evaluated at this, but then you get that minus 1 times minus 1. Okay, so that is that. So v solves the wave equation. And there is nothing special about x minus t. You can actually take x plus t also. So this is another observation, that you give me any smooth function g, and using that smooth function g, which is a real valued function of one variable, you define a new function v of two variables, essentially g of x plus t. Same idea. You can show that v also solves the wave equation. Okay? So in these two slides, it may sound like this equation has got excess of solutions, because there are so many options to write down solutions. You can pick any arbitrary smooth function f, you can build a solution to the wave equation. Any arbitrary smooth function g, you can build a solution to the wave equation. And in the previous slide, we made one more useful observation, that if you give me a solution, two solutions, I take the linear combination, that's again a solution. So if I call u of x comma t, this new function, as just an arbitrary function f evaluated at x minus t, and another arbitrary function g evaluated at x plus t, from whatever we have been convinced so far, this fellow will also solve the wave equation. Okay? It turns out that a general solution to the wave equation should look like this. That we will see later on in afternoon's lecture. Okay? So this is the one-dimensional wave equation that we are trying to understand. Okay? Your x runs in the whole of R, and t runs in the whole of R. I hope this is clear. These are just consequences of what we know from calculus. There is nothing much to this. So you have to just do those composition rules and differentiate and check. Okay? Okay, so now let's move on to, okay, so we are going to take a viewpoint of understanding solutions to the wave equation slightly differently, in the sense that, you see, when we were studying the transport equations, we were very eager to write down the solution. We were like, okay, how do I find the solution? How do I find the solution? For the remaining time of this lecture, I want to convince you that you can say a lot of intelligible things about the solutions to the wave equation without even actually solving it. Okay? Not actually solving it, you will be able to say something like non-trivial about the solutions to the wave equations. That's what I want to impress you on. So now, for that we need some tools from calculus. Okay? I will state those things, and if you don't remember how they came, let us just trust them. Okay? That they are true, because Wikipedia has them, so that should not be wrong. Okay? So we will just trust them and use them to build upon something. Okay? So you give me two differentiable functions, f and g. There is something known as integration by parts formula. Okay? Integration by parts formula says essentially this. You are given two functions on the interval ab. You take the derivative of one function, multiply by the other function. So f prime g, if you integrate on ab, this fellow should be equal to the negative of integral over ab of f times g prime. You see, you have just thrown the derivative onto the other guy. That makes you bring this minus 1. And then these are evaluations at the endpoints of your interval of integration. Okay? So this is known as the integration by parts formula. And this is just a simple consequence of differentiating a product, okay, and the fundamental theorem of calculus. Okay? So we all know this, right? If I take a product of two functions, f prime, f and g, I differentiate the product, it is f prime times g plus f times g prime. Now if you integrate this from a to b, you are integrating right hand side also from a to b. By fundamental theorem of calculus, when I integrate this fellow, this is just f evaluated at b, g evaluated at b, minus f evaluated at a, g evaluated at a. This is just from fundamental theorem of calculus, and you keep this fellow on the right hand side. And that is the integration by parts formula. So nothing spectacular about that. So, but it's, some people are of the opinion that you can do a lot of things in partial differential equations if you know this formula. So usually you are just playing around with the integration by parts formula. So let's just remember this. And then let us take two differentiable functions. Now a and b are now real valued functions of one variable, and f is a function of two variables, real valued functions of two variables. So then there is something known as the Leibniz integration rule. Okay. So Leibniz integral rule comes in when you are trying to differentiate some quantity, actually an integral, where the variable against which you are trying to differentiate, that is like your limits of integration also depend on that variable. So you see, you are trying to differentiate with respect to t, and the limits of integration are also functions of t. So when I write this down, there is an inherent assumption that a of t is always less than b of t, so that it makes sense. So that is all there. So the way to remember this Leibniz integration rule is what's happening here. There are three terms when you differentiate this term. Okay. So if we didn't know, like, what is the obvious thing that we would like to do? We would like to take the derivative inside and differentiate the integrand. Okay, there is that term sitting here. Okay, that is that. But there is some terms that you need to add also. If a and b are just constants, then these two terms will not contribute, because you see there is a derivative of b and there is a derivative of a. So if a and b were constants, our intuition is right. You can just blindly take the derivative inside. But if these two things are functions of the t variable, then you have to add these two terms. This first term is just evaluation of this integrand at the topmost endpoint, that is b of t, multiplied by the derivative of the topmost thing, then minus, same, you take the integrand, evaluate at the bottommost endpoint, and multiply by the derivative of this. That's it. Okay, so we will try to remember this formula. And then we will be needing this. Okay, these two things, you give me any two real numbers, the product of these two real numbers AB is bounded from above by a square plus b square upon 2. Similarly, the negative of AB is also bounded from above by a square plus b square upon 2. This is just a simple consequence of our algebraic identity. A plus b whole square is greater than or equal to 0, and a minus b whole square is greater than or equal to 0. Okay. Anybody can say this, even the school kids will write this, that it should be greater than or equal to 0. And in school we study what is a plus b whole square and what is a minus b whole square. And those two things are essentially consequences of that. Okay. So, using these three things, we will prove a very interesting thing about solutions to the wave equation. Only these three things, nothing more. Okay. Okay. So, before that, we will introduce a region in R2. We call it a triangular region in R2. Okay, as the name suggests, it's a triangular region. Okay, for that we will pick some point x0 in R and some t0 positive. So this is the picture. So we have got this point x0 t0. Because t0 is positive, it is sitting in this upper half plane. So you have got x0 t0. So what you do is, and then this is x0 comma 0. Okay, you go to the left by t0 amount. So this is x0 minus t0, and to the right you go by t0 amount, the same t0 which is in the t-axis. This is x0 plus t0. So you get three vertices, x0 plus t0 comma 0, x0 minus t0 comma 0, and x0 t0. Using these three vertices you form a triangle. Okay, and you take the region enclosed by that triangle. So this is the triangular region that we are interested in. Okay, it turns out that to understand the wave equation, this triangular region plays a very important role. Okay, to understand the solution of your wave equation at this point, somehow you need to know something about this triangular region, and that's what we will try to prove now. Okay, so see what's happening here is that if I got this triangular region. Okay, so this is where x0 t0 is. And this point is x0 minus t0, comma 0, and this is x0 plus t0, comma 0. Okay. Now, if I take a slice parallel to the x-axis here, I'll hit at 2 points which are on these things. Okay. So, it will be like x0 minus t0 plus t, comma 0. Oh, sorry. It will be something. Okay. Comma t. And this will be x0 plus t0 minus t, comma t. Okay? Like these 2 points. Like when I keep varying t, what I am doing is, I'm taking x naught minus t naught minus t. That's what I'm taking. When I take t is equal to 0, I'm sitting here. Okay? And on the right hand side, I've got this point x naught plus t naught minus t. Okay? So when I take t is equal to 0, I'm at these 2 points. When I take t is equal to t naught, I'm at this point. So when I vary t from 0 to t naught, I'm actually covering these lines, right? I go until I reach the top. So if I consider these intervals, x naught minus of t naught minus t, comma x naught plus t naught minus t, I'm actually moving along like this. Okay? I cover the whole triangle. And this is a picture to keep in mind, and I'll leave that picture. But for now, let's take this triangle. You give me any point x naught comma t naught with this property that t naught is positive. We can always consider this triangular region, okay, with these 3 vertices. Okay, this is a very famous principle associated with the wave equation. This is known as the causality principle. And it says the following. Suppose there is a solution to this wave equation. Okay, suppose somebody tells you that, okay, there is a function u of x and t variables such that it solves this wave equation for every x in R and for every t positive. Now, pick any point x naught in R and any t naught positive. Pick any, okay, so that you can talk about this triangle. And then suppose your u and the time derivative of u on this part of your triangle, the bottom part of your triangular region, here. This is what corresponds to t is equal to 0, right? So you are saying that u at x comma 0 is 0 and the time derivative of u at x comma 0 is 0. For which points x? For all those x which lie in this interval, x naught minus t naught and x naught plus t naught. That means for all those points on the bottom of this triangular region, your u and the time derivative of u are 0. Suppose it is given to you. Just because u solves the wave equation, you can actually say that if this line happens, if u and the time derivative of u vanish on the bottom of the triangle, your u should vanish everywhere in this triangle. Just because u solves the wave equation. Okay? What happened? Something is going on. Should we do something? Okay. Yes. So, this is known as the causality principle. It tells you that if there is a function u which solves the wave equation on r cross 0 infinity, and in this interval, x naught minus t naught and x naught plus t naught, if your u and the time derivative of u vanishes, okay, at the level time t is equal to 0, then that u should vanish everywhere in this triangle C. Okay. So for us, whenever we say that a candidate u is a solution to the wave equation, we require it to be twice continuously differentiable. Okay, we are always taking, whenever we say that, so that it makes sense. Okay, and that equation should be satisfied everywhere, in R cross 0 infinity. So this is our notion of solutions. This is just to make precise what we are talking about. Okay. So we will try to prove this result, this causality principle, and without using any structure of the solution. Okay. We will only use the fact that there is a function which solves the wave equation. That's it. And those 3 things that we stated from calculus. Only using those 3 things we will be able to prove this result. That at time t is equal to 0, if your u and the time derivative of u are vanishing on an interval, exactly this particular interval, x naught minus t naught and x naught plus t naught, then on this triangle, your u will be identically 0. Okay. So, before we try to prove this causality principle, I would like to contrast this wave equation with the heat equation that you guys have been studying. Okay? So in the context of heat equation, you have been seeing what is known as the initial value problem. So this is the heat equation. The only change when it comes to the heat and the wave equation is, in the heat equation you have got only first order time derivative. But in the wave equation you have got second order time derivative in the equation. That's the only difference. But somehow it makes all the difference for the solutions. So this is the heat equation. And when somebody talks about initial value problem, they want you to specify, because so far you see we never talked about any data for the wave equation. So in the heat equation, they want you to specify what is the value of the temperature, because this is supposed to model a temperature evolution. So the temperature at time t is equal to 0. You specify the temperature at every point in your domain. So in this lecture, our domain where x runs is the whole of R. Okay, we will not worry about the boundary conditions and all, so that's why we are doing it in the whole of R. So you specify what is the value of your temperature at time t is equal to 0 at every point in your domain, and you want to understand how the temperature evolves as t goes to, t becomes larger and larger. Okay. In the context of wave equation, when we say, okay, we are studying an initial value problem, we have to specify two things. Okay. In the heat equation, you have to specify only one thing, because you have got first order time derivative. In the wave equation, because you have got second order time derivatives, for those of you who remember from your ODE days, where when you are studying a second order ordinary differential equation, initial value problem corresponds to assigning two values. You will assign what is the value of y at 0 and also y prime at 0. So the similar thing has to be done for the wave equation. When we say that we are studying an initial value problem for the wave equation, this is the wave equation, we have to specify two things. We have to specify something known as the initial displacement. Okay, that means when time t is equal to 0, what is u at every point x. And also we have to specify something known as the initial velocity. Okay, these are just terminologies for what u means and what the time derivative of u means. If u is the displacement, its time derivative represents the velocity, and so you are also giving what is the initial velocity. So that's the ut at x comma 0 when time t is equal to 0. This is you have to assign the velocity at every point x in your domain, the spatial domain. So you assign these two functions at time t is equal to 0 for u and the time derivative of u, and then you ask, as time evolves, what happens to the displacement u, okay, which solves the wave equation. So this is the context. And if you go back to causality principle, they are essentially telling something about this u0 and u1. Because you see, in the causality principle, the condition was on u at x comma 0 and ut at x comma 0 vanishing in some interval. Okay? And so causality principle says, if in your initial value problem, if the data has this property that it's vanishing on an interval, there will be a triangle in which the solution will be seen. Okay? So these are the few comments that we would like to make. Causality principle essentially says that if the data u of x comma 0 and ut of x comma 0, they vanish on the bottom of your triangular region, your displacement u is 0 in the entirety of your triangular region. Okay? So this is what causality principle is telling you. And somehow this causality principle does one more very important job. It helps you decide or deduce uniqueness of solutions to the initial value problem. By that, I mean the following. You see, we are talking about this initial value problem for the wave equation, right? That means I have to assign two functions, u0 of x and u1 of x. u0 of x for the initial displacement and u1 of x for the initial velocity. And then you ask, okay, can I find a u which solves the wave equation, and when I take t is equal to 0, I get back those two functions, u0 and u1. Now, it is always helpful to know whether this particular problem can be solved uniquely. Like if there are multiple solutions for a given data, there is something wrong with your model. You are not modeling the right phenomena. So this is the first question we need to fix, that given a data, there is a unique solution to your problem. Okay? And that is this theorem. And this uniqueness simply follows from this causality principle that we have just stated. We have not proved it yet, we will try to prove it. But using the if we trust the causality principle about this triangle, you can actually prove uniqueness to this problem. It says the following: you give me two functions, u0 and u1, continuously differentiable functions, okay? u0 and u1 you take. These are just functions of the x variable, real valued function. Then you consider this initial value problem. You are looking for a function u which solves the wave equation, such that when you take t is equal to 0, in u you get back this given function u0. And if you take the time derivative of that solution u and you fix t is equal to 0, that is just a function of x, and you should get back your given function u1 of x. So the punchline of this theorem is there can be at most one solution to this problem. If you are given u0 and u1, these two functions, there can be at most one solution. Okay? There is a word of caution here. This result does not guarantee you that there is a solution. This is telling you that there cannot be two solutions. Okay? If you give me u0 and u1, there can at most be one solution. Okay? So it essentially means that if there is some other guy who comes and tells, okay, there is a solution to this problem, you can just take the solution that he has. You need not go and look for one more solution, because this theorem tells you that there cannot be two solutions to this problem. So once you find one solution, you are good enough. Okay? So that is what this theorem is telling you about uniqueness. It turns out that this uniqueness proof is a simple consequence of this triangle thing that we have just stated, the causality principle. Okay? And when it comes to proving uniqueness results in differential equations, no, we do the most obvious thing that you can do. Okay? You prove by contradiction. So you see, we are supposed to show here that there cannot be two solutions, right? So what you do is, you suppose that there are two solutions and you subtract them. And you show that the difference is identically 0. Then you have shown that any two solutions to this problem should look alike. Okay, so this is what we are trying to show. Okay, so, and believe it or not, this is how you try to prove uniqueness for any differential equation that you come across, most of the times. Okay, our advancement in knowledge has reached only this much. Okay, you prove uniqueness, you take two solutions, you take the difference, and you show that they are one and the same. Okay? Okay, so this is the proof of uniqueness. It just fits 2 slides, and the idea is whatever I have told you. Suppose there are two solutions. You call them u and v. Okay, these two functions u and v, and you are assuming that both of them solve the same initial value problem. That means both of them solve the wave equation, and both of them satisfy the same data. U at x comma 0 is u0, and v at x comma 0 is also u0. And time derivative of u at x comma 0 is u1, and time derivative of v at x comma 0 is also u1. Then what did I say? You take the difference, right? So let us take the difference of these two and call it a new function w. So w is just the difference of these two functions, if at all they exist. Now, what is the equation satisfied by w? We said something about in the very first discussion we had today. If you give me two solutions, any linear combination is also a solution. So w also solves the wave equation. W solves the wave equation. Because both of these guys are satisfying the same data, and because I'm taking the difference, the data for w is 0. And the data for the time derivative of w at t is equal to 0 is also 0. Okay? And there is an obvious candidate staring at us, and that's the 0 solution. You can, 0 solution, I mean the function equal to the constant 0 solves all of these things. Our claim is that is actually the case. W should be identically 0. Okay? This is our claim, that w is this constant function equal to 0 everywhere. Okay? Now, let us, you see, right now we are all trusting in this causality principle about the triangles. Okay? Somehow we will contradict this fellow. Okay? So we are supposed to show that w is identically 0, and w solves the wave equation. Right? W solves the wave equation. And causality principle is about the guys who solve the wave equation. Now, suppose that is not true. Suppose w is not identically 0. That means you can find a x star and t star such that this should not be equal to 0. Sorry guys, okay? This is what happens when you type the slides just before you come to the lectures. Okay? So I was typing it this morning. So this is not equal to 0. Okay, so please read it like that. We will change that before we share it with you. So suppose there's a point where W is not equal to 0. And now what you do? You pick that point x star t star and you take this triangle associated with that point x star t star. You take that point x star t star. So the triangle will have these two base vertices, x star minus t star and x star plus t star. Now, what do you know about the data for W? Data for W is 0, right? W is 0. When t is equal to 0, W is 0. And also the time derivative of W is 0 when t is equal to 0. So, W and the time derivative of W is 0, in particular on this red part, the base of this triangle. So, if you believe in causality principle, it is 0 everywhere. In particular, it is 0 at this point also. So, this contradicts the causality principle, okay, if W were not vanishing at a point. Okay? So, you contradict the causality principle. This particular assumption contradicts the causality principle. So, that is not true. So, W is identically 0. Okay? You see, this is just a simple observation using the causality principle. We have not, of course, proved this result about, if you vanish on the bottom of a triangle, you should be 0 everywhere. But using that fact, we have just proved that your initial value problem for the wave equation cannot have two solutions. It can have at most one solution. What is that solution? We will see in the afternoon's lecture, okay? Because now we have convinced ourselves, I hope, that there cannot be two solutions for an initial value problem for the wave equation. Is that clear? It's just banking on the causality principle, okay? Now let's try to prove that causality principle, which is very important, okay? So for that, we will consider this particular function, okay? So as I told you, we will be proving the causality principle using only three things. The integration by parts formula, the Leibniz integral rule, and that identity which comes out of this a plus b whole square is greater than 0 and a minus b. Only using these three things we will be able to prove it. And the first ingredient in the proof starts by defining this function, okay? This function e, which is a function of the t variable, which runs from 0 to t naught, okay? In the statement of the causality principle, there is that t naught, no? It's the same t naught. Okay? So we have to show that u is vanishing in that triangle. So what are we doing here? We are taking that solution u to the wave equation and taking its time derivative and its spatial derivative, and we are simply squaring each one of them and adding them, okay? And we are integrating between these 2 points. And if you remember, these 2 points are essentially these points here, okay? So please try to look at it carefully. It's x naught minus t naught minus t and x naught plus t naught minus t. In the very beginning, when we introduced this triangle picture, we told you that when t is equal to 0, this is just these points. That means when t is equal to 0, you are integrating ut square and ux square on this red line, okay? When t is equal to something between 0 and t naught, you are integrating that function ut square plus ux square on this line. You are simply integrating those functions. So essentially, when little t runs from 0 to t naught, you are integrating along each of these lines. There are infinitely many of them. You are simply integrating. This is what is happening, okay? And this e of t is essentially doing that. E of t integrates this quantity because u is a solution to the wave equation which is given to you, okay, everywhere in r cross 0 infinity. So you simply take the square of ut and the square of ux. This sum you are integrating along each of these red lines, okay? That's what et does. E of t, for a given time t, it integrates and gives you. There is this factor of half also. You will see why the half is there very soon, okay? Now, what is happening in E? You are integrating non-negative quantities. So it's a non-negative function. Okay, first thing is that. And also another thing is E of 0 is 0. Can you see that? Because in the statement of the causality principle, what did we say? U at x comma 0 is 0 and ut at x comma 0 is 0. That is given, that in the base of this triangle, your u and ut are 0. And if your u is 0, you are differentiating with respect to x, that is also 0. Okay? So you are actually summing two zeros there. So when you integrate, you get 0. So this is the first observation, that E of 0 is 0. Okay? So that means when you are taking the integral along this line, it is just 0. And the second observation is that E is non-negative, because it's just integrating non-negative quantities, so it should be non-negative. So if we manage to show that this non-negative function is actually identically 0, okay, that will do the job. Let me explain. So if we show that this fellow, this function that we have defined, is actually a 0 function from 0 to t naught, that means what? If this is a 0 function, that means this integrand should be 0 from 0 to t naught, that integrand. Okay? And if that integrand is 0, it's just derivatives. Ut equals to 0, ux equals to 0. You have got a function of two variables whose gradient is 0. That means the function has to be a constant. Is that clear? So this is again from calculus. How do you show that a function is constant? You have to just show that the gradient vanishes. And that, this is the gradient of that function of two variables, and that can be deduced if we manage to show that this function is identically 0, which helps us decide that the integrand should be identically 0, and that's the sum of two square terms, so each of them should be identically 0. So that's how we get that. Now, from here we can only conclude that this function u should be equal to constant. But because u is 0 on the bottom, and we are assuming continuity of functions, that constant should be equal to that 0. Okay? We will deduce that u must be a constant, and that u should be 0 because on the bottom of your triangular region you are 0. It is given. And this is how we prove. So we will eventually show that E is a 0 function from 0 to t naught. Is the strategy clear? And now our goal now is to just show that this horrible looking expression is a 0 function. Even though we have made it look overly complicated, there is nothing in it. It's just a 0 function. Okay? We have to eventually use the fact that u solves the wave equation. We have not used that, so we will use that. Okay? So, in the last 4 or 5 minutes, we will finish. Sorry about that. Now, okay. You got this expression. Let me just write down this expression, and then we will. Yeah, because this is from x0 to x0, that will also be 0. Yes, yes, yes. So, now, you have got this E of t, I just write down this 1/2 of x0 minus t0 minus t and x0 plus t0 minus t. Okay? And you have got ut squared here and ux squared here, dx. Okay? Now, we have got a function which is starting off at 0. Okay? And we will show that its derivative is less than or equal to 0. That means it is a non-increasing function. Okay? And because it's a non-negative function, it starts off with 0, you stay 0. Okay? Now, we have differentiated this function in the t variable, this particular function in the t variable. This is where we have to use the Leibniz integral rule. Okay? Because the two endpoints are functions of the t variable, so we have to use that formula that we wrote down. Okay? So, what did that formula say? You have to evaluate this integrand at this point, at the topmost point, and then differentiate that fellow with respect to the variable. So that is the first line. We have simply evaluated the integrand at this point, x0 plus t0 minus t, and then we have differentiated that fellow with respect to the t variable, which will give you a minus 1. So that's why there's a negative sign here. Okay? Then you have to subtract the evaluation of this guy at the bottom point and then differentiate with respect to t. But that gives you a 1 here because there's a negative sign, negative sign. So there is that subtraction will give you a negative sign. Please note that these two things are evaluated at two different points, one at the topmost and the other one. And then there is a third term in the Leibniz integral rule where you blindly take the derivative inside. So when you differentiate the square of ut just by using the product rule for differentiation, you get 2 times ut times utt, and that's why. And this is the reason why you put a half there, so that it takes care of the 2 that comes here. And when you differentiate this, you get 2 times ux times uxt. Okay, you get this. Now, in this step, we have only used the Leibniz integral rule, nothing spectacular. Next, we will just keep these two things intact. We will not touch them. That thing will come later. I promised you that we are going to do an integration by parts formula. Okay. Now, we will do an integration by parts in the x variable. This is an integration in the x. Here there is no derivative in x here, so it's not meaningful to do anything with integration by parts here. So we'll do integration by parts here. We'll throw one of the derivatives in the x variable onto this other guy. Okay. When you do that, you see integration by parts, we wrote down here, right? F prime g plus f g prime integrated from a to b is just this guy. Okay. Now, going from, you see here, I take ux to be f and then ut to be g. Okay. Then you just apply this particular integration by parts formula. You throw one of the derivatives which will give you a negative sign, okay? And then there are these two boundary terms which are just these two guys. We call f as ux, g as ut, right? So ux evaluated at b times ut evaluated at b, which is this fellow, minus same ut evaluated at the bottom point and ux evaluated. So you get this. Please note that here you have got the sum of those guys with the squares and you have got the product of them. This is somehow hinting that you have to use these identities. Okay. And here, until now, we have not used the fact that u solves the wave equation. So this is the stage where you will use the wave equation property of u, because you can factor ut out of this. So what you will be left with utt minus uxx, and that is identically 0. So this integral term goes away. Okay, so that's what we will say here. Using the fact that u solves the wave equation, you are just left with these boundary evaluations after you have done the integration by parts. And then you have got the product now. A times b, I can write 1/2 of a square plus b square. That's what I have done for this product. And for this product, I have again used the same identity. I get this. Okay. AB is bounded from above by a square plus b square upon 2, and minus AB is also bounded by a square plus b square upon 2. So using those two things. So if we go back, this is what we had. When we differentiated E, we got those two boundary terms from the Leibniz integral rule, and then there was this integral term. And we did an integration by parts in this integral term and got rid of the integral term altogether, and we got an inequality. Okay, and that inequality, that upper bound, was actually this guy's, but with an opposite sign. If we go back, sorry, see, there's a plus sign everywhere. It's exactly the same expression. Okay, when I share the slides, you'll be able to recognize that. It's exactly the same expression, but with an opposite sign. Okay, so here we have got an upper bound for this. So we bound this from above by the same similar looking guys, but with an opposite sign. So when you put that upper bound, all these things, they cancel off. So you will be left with this guy, that E prime of t is less than or equal to 0. So it's a non-increasing function, A non-negative function which is non-increasing, which starts off at 0, should stay 0. Okay? And that's how you get E of t is 0. Okay? Non-negative, we conclude E of t is 0. And we already argued that if you show E of t is 0, then the integrand should vanish. That means the gradient should vanish. That means the function should be constant. And because the function is constant on the bottom, it should be that 0 function. Okay? So this is a wonderful property of the wave equation, that you pick any point, x0, t0, you draw this triangular region. If you a priori know that your function and its time derivative is vanishing here, you can comfortably say that your solution will vanish here. See, this whole thing we are able to say without having access to the solution itself. We do not have any expression for the solution. We just did 3 elementary things from calculus and we are able to say this. Okay? Okay. There is one more thing, but this I will continue in the next lecture. We are running close to the lunch time. We have that luxury today. Yeah, thank you. Any questions so far? Okay. Thank you, guys. Okay. There was something in the chat that was a question? No? Oh. So welcome back after the lunch break. So I have the task of making sure that all of us don't go take a nap. This including myself. So this is just continuation of what we were discussing earlier. Okay. So I hope you are able to appreciate this property on the triangles. That the solutions to the wave equation satisfies. Okay. We will try to do something similar now without actually having an analytic expression for the solution to the problem. We will say something about the solution, and for that we need one more tool from calculus. Okay. So that I'll just state. So if somebody gives a real valued function on the real line and they tell you this integral of f square is finite, that essentially means that it necessarily your f should vanish at infinity. Okay, so it cannot grow at infinity. It cannot have any mass at infinity. That's what it means. Otherwise, this fellow will not be finite. So in other words, we are saying that if you let, if you start looking at the values of f for larger values of x, it's going off to 0. Okay? Because if this does not happen, this is not possible. So that's what. Let's just keep this in mind. So whenever we are trying to integrate, square integrate some fellow, that we are essentially assuming that that fellow is dying off at infinity. Okay? And a very nice class of functions for whom this is actually true is these functions which are known as compactly supported. Okay. In the problem sheet that we gave yesterday, we kind of stated this phrase, a function is compactly supported in R. That's a fancy way of telling this thing, this line. Okay. If we say that a function is compactly supported in R, we essentially mean that you can find a closed interval AB, a finite length closed interval AB, such that outside that interval, your function is essentially 0. Okay? Anything non-trivial regarding that function is happening inside that closed interval AB only. Okay? Outside that interval, it's just a 0 function. So whenever that thing happens for a given function, you say that function is compactly supported on R. Okay, so this is our terminology. And any smooth compactly supported function on R will have that square integral finite. Okay? For various reasons. We will not get into that. We will just admit these things. I keep telling you, right? We are not aiming to become like experts who know everything. We will just pick a problem and try to understand that. I think that's the new trend these days, and we will embrace that. Okay, so now this energy conservation. We did something about the triangles, okay, that's one property of solutions to the wave equation. There's also something known as energy conservation, okay. For that we need to introduce some notations, and I'll introduce that. So suppose you take this solution u to your wave equation, utt equals to uxx, okay. With this data, we know that for an initial value problem for the wave equation, you need to give two functions, u0 and u1. So, and you are assuming that u0 and u1 are compactly supported, in that sense that anything non-trivial is happening inside a closed interval for those two functions. Now then, using that function u which solves the wave equation, we define this function k, which is a function of the t variable. What are we doing here? We are taking the time derivative of the solution and squaring it and integrating in the x variable. Because this is a function of x and t variables, we have integrated out the x variable, so what is left is a function of the t variable. And we are throwing in a half here, you will realize why later on. So this is just a function of t, okay, the time variable. And similarly, we introduce this function p. We almost do the same exact thing, but now we are squaring the spatial derivative of that solution. So earlier for k we squared the time derivative of the solution and integrated in x. For this function p we square the spatial derivative, the x derivative of the solution, and integrate in x. So we have got these two functions of the time variable, and these fellows have got a name, okay. This k is usually referred to as the kinetic energy. Yes, yes, it's just a function of time. T. This guy. You are integrating out the x variables.
In both you are doing x.
Yeah. In both you are integrating out the x variable. So what is left is the t variable. Okay. So this k is referred to as the kinetic energy of the system. Okay. These are just names. We need not remember any of it. P is referred to as the potential energy of the system. Okay. So from our physics days, we remember that if you have got a kinetic energy of the system and the potential energy, you add them up, you get the total energy of the system. So essentially, we add these two things, we get the total energy of the system. If you remember the way we proved this fellow, this triangle, this causality principle, we were actually integrating these fellows only. This ut square and ux square were integrated on these intervals, right? At every time t we were integrating. Some of these are all interrelated. So one thing to observe is that at time t is equal to 0, this is just ut x 0. And we know what is ut x 0, that is u1. That's given function. So k of 0 is just this quantity which is known to us. This is some number now. This is not depending on t anymore. Similarly, p of 0 is just ux x 0. We are given what is ux 0, and you have to simply differentiate it in the x variable, and that's what we have done, and square it. Okay, you have computed the square integral of the derivative of your initial data u0 and divide by 2. So k0 and p0 are known, okay, and you want to essentially know how the k and p evolve in time. Okay, that's what we are after. And as I told you, whenever you have got kinetic energy and potential energy, you sum them up, you get the total energy of the system. So that we call E. We tend to like this letter E for any function of t. We called E earlier, this one. We are calling this also E. So just bear with me on that. So there is some conservation happening, as the title of this slide suggests. There is energy conservation in this system, and that we will make precise in the next slide. Okay? Conservation of total energy. So let us start with two nice compactly supported data, u0 and u1, which go into your wave equation, initial value problem. And taking these two functions as data, you suppose that there is a solution u to this system, initial value problem, which solves the wave equation with this data. Then you consider the total energy associated with that system. See, by that I mean you are essentially considering that integral, that E of t. right? So let me just write it here. Oh, this is not going away. I wrote with a lot of energy, I guess. I'll write here on top. So E of t is just 1/2 of integral of ut square. Oh, this will work. Oh, yes. Something to spray maybe. You can come and bring and keep it here. I will try to, oh, you hold on top of it. Give it ux square dx. Okay, on R. So, the punchline of this theorem is that if you consider that function, no, that E of t associated with the solution to this problem, it's a conserved quantity. More precisely, we mean this. E of t is always taking the same value. It remains constant. It's equal to E of 0. Okay? That means the energy in this system is not changing with time. The total energy is conserved in this system. Okay? So, your total energy of the system is essentially decided by this U0 and U1. As we saw earlier, using U0, you can say what is P of 0, and using U1, you can say what is K of 0. And adding K of 0 and P of 0, you get E of 0, the total energy. And it turns out that at any other future times t, your total energy of the system is essentially what you begin with. Okay? So this is a wonderful property about heat equation, that the energy is not lost in the system. Okay? So this is unlike what the other equation that you are studying, which is known as the heat equation. There energy dissipates. Energy will die out with time. But here energy is conserved. And this again is a simple consequence of that integration by parts formula. Nothing spectacular. Okay? The resulting thing is spectacular, not the technique used. Okay, so that's what. So we will try to prove this energy conservation property. And whenever we want to show that something is a constant function, the best way to show that is you differentiate and show that the derivative does not change. Okay? So you have got a function of the t variable, and the assertion of the theorem is that this is not changing with time. It's remaining the same it begins with. So you just differentiate with respect to time. And this computation we did earlier. You have got ut square here, ux squared here. You blindly take the derivative inside. Okay? So 2 times ut, and the 2 which comes when you differentiate this quantity is cancelled by the 1/2. That's why you keep the 1/2, so that you need not carry these constants every time. So you get this. And what did we do last time? We did an integration by parts in this term. Because there is uxt, we threw one of the derivatives onto this. And in order to do integration by parts, maybe I rushed it last time, you have to have 2 functions. Okay? So there is ux, then there is uxt over r. We are claiming that we have to do integration by parts here. So we have to talk about 2 functions. Our first function f is ux, and the next function g is ut. Okay? And you do the integration by parts formula that we have derived. Blank. Okay. Yes, I will. Okay. When you do the integration by parts with these choices of f and g, so now one of the derivatives here will go there. So you get minus uxx ut over r. And in essence, you should also get boundary terms. Okay? But you are on the entire real line. And as we know from calculus, whenever we are integrating over the entire real line, we are essentially not doing the entire real line, we are computing these integrals, these limits, limit L going to infinity of minus L to L, some function, f of s ds. See, whenever this limit exists, then we say that the integral over r of f is finite. So this is what is happening here also. So we have to essentially write this integral over r as this limit L going to infinity of this. And on minus L to L, you do this integration by parts trick on the closed interval. But as we said earlier, if your solution is compactly supported, when L becomes larger and larger, you will get to this bigger interval where the boundary terms are essentially not contributing. So the boundary terms do not contribute when you do integration by parts here. Okay? You get only this and there is no other contribution. And once you are here, we know the easy way out. You can factor u of t out, ut out from each one of them. You are left with utt minus uxx. And u is a solution to the wave equation. So this term is vanishing. You see, this is just one integration by parts. And it lets you, and the boundary terms are not contributing. You see, we assume that u0 and u1, the initial data is compactly supported. But here, when I made the statement that the boundary terms do not contribute, we are essentially assuming that your solution is also compactly supported, and we have not used that fact, we have not proved that fact yet. We are admitting that here, and in this lecture only we will actually prove that if you have got a wave equation with initial data which are compactly supported, your solution will also be compactly supported. Okay? So that we will see very soon. So that is used here. For now we will just admit that. And then you get this. Because u solves the wave equation, you get this and that is that. You see, it just fits one's beautiful slide to show that the energy of the associated with the wave equation, it is not dissipating or increasing. It is just remaining constant. Okay? This is a wonderful property of the wave equation. Okay, so now I hope I have convinced you that without having actually the analytic solution at hand, you can say something very nice things about the solutions to these equations if you assume that they exist. Okay? And we also proved earlier that there cannot be two solutions to this problem. We have not done the most important thing to show that there is a solution to this problem. And now we take inspiration from the work of D'Alembert, who actually derived the solution to this problem. Given any u0 and u1, he gives you a recipe for writing down u of x comma t. Okay? So this is what we will do for the next 3 to 4 slides. Okay? It's a bunch of calculations which anybody who has done a basic calculus course can follow. Okay? It's just making a change of variable and integrating. Okay? So just bear with me. And this is the most general wave equation on the real line, in the sense that we have thrown in this constant also, c square. C is just some positive number, fixed, constant. Okay, C is just a constant. Now, D'Alembert's idea was essentially this. You see, D'Alembert wanted to write down u of x comma t. See, you are given this problem. Okay, a very practical thing to ask is, what is the expression for this solution, u of x comma t? Can I write this in terms of that u0 and u1 which is given to us? Because that is the data. Somebody tells us that this is the given u0 and u1. Using those two things, can we write an expression for this? So D'Alembert starts like this. He introduces new variables, okay, which essentially involves the old variables from where this problem is posed, x and t, and also that c which is there. Okay, so using that he introduces x minus ct and x plus ct. Okay, x minus ct he calls as psi, and x plus ct he calls as eta. Okay, this is a nice change of variables which goes from R2 to R2. Okay, so in order to decide something is a nice change of variables, you have to compute the Jacobian matrix, which we did yesterday, and we will just compute. Because this is going from R2 to R2, you have to compute 4 partial derivatives, and that's what we do here. So d psi by dx is 1. Okay, this is what I said, this is just elementary basic calculus. And d psi by dt is minus c. d eta by dx is 1, and d eta by dt is c. Okay, you have got all those 4 components of the Jacobian matrix to claim that this is a nice change of variable. Now, what you do is, you are starting from a point x comma t in your original coordinates. Yeah, this is what we are supposed to do to stay with the whiteboard. Once you write, you erase. Okay, I just left it like that and that went back. So, for every point x comma t, you are associating a point psi comma eta. Okay. Now, in this coordinate system psi eta, we introduce a new function v. Okay. This v, what it does is, this v at the point psi eta is essentially u at the point xt, because this psi eta is related back to some x comma t in the xt plane. Whatever the value of that solution u at this point is, you assign the same value for v at this point. Okay, so for a nice change of variable, this is doable because any point on the psi eta plane is related back to xt plane by that map. So this is a well-defined function. You give me any psi eta in r cross r, I can always do this assignment because there is the corresponding point xt in the xt plane. Okay. Now the essential idea is you have got this xt plane and psi eta plane. Okay. And in the xt plane you have got this function u which solves the wave equation. Now if v and u are related like this, if u solves the wave equation in the xt plane, what does v solve in the psi eta plane? That is what we are going to find out. This is equivalent. Okay, if u solves the wave equation in the xt plane, that is equivalent to saying v solves some other equation in the psi eta plane. The credit goes to D'Alembert because it turns out that the equation which v solves in the psi eta plane is very easy to integrate, and that's why this whole thing is very important. Okay, so I have given away the surprise, so let us try to do the computations now. Now this is very straightforward. We have to just use the fact that u solves the wave equation. So u solves the wave equation, so you need to compute the second order derivatives of u in both x and t variables, and that's what we will do. First let us compute the first order partial derivatives of u in the x variable, and this is just chain rule or composition rule, whatever it's called, because v of psi eta, right? So u of x comma t, u of x comma t is v of psi eta, and psi and eta are related to x and t. So when you differentiate u with respect to x, you have to differentiate v with respect to x also, and that's what we do. V differentiated with respect to psi, then psi differentiated with respect to x, then v differentiated with respect to eta multiplied by eta differentiated with respect to x. And we already know what is d psi by dx and d eta by dx. Okay, and using that we get this, because those two are just one, because that was x minus ct and x plus ct, those were the change of variables. So you get this. You have got an expression for du by dx, but you are after d square u by dx square because u solves the wave equation. It's the second order derivatives are involved. So now you have got this function which is a function of psi and eta. Okay, you do the same exact thing. You first differentiate with respect to psi, that function, times d psi by dx. Then you take the same function, differentiate with respect to eta, multiply by d eta by dx. But d eta by dx and d psi by dx are one again, and now you just push this fellow inside. Okay, when you push it, you get this term. There are two terms here which look like d square v by d psi d eta. One comes from here, and one comes when this fellow hits this. Okay, and you are assuming that these are very nice functions, so it doesn't matter in which order you differentiate, and that's why, you know, the mixed partial order derivatives are the same, so you get two copies of it. Okay, so d square u by dx square is, in terms of v, it is this in the psi eta variables. Now you do the same thing in the t variable. Okay, because you have to compute d square u by dt square. Du by dt, again chain rule or composition rule, so you get this. But d psi by dt is minus c, and d eta by dt is plus c, I believe. Yeah, so this is the thing. Okay, and you don't stop here because you need second order partial derivatives with respect to t, and you go on and you do the same exact thing. You got that function which is a function of psi and eta, do that, and you get this expression. Okay, now we know that u square uxx is utt, so you have to equate these two things now. So you have to equate these two things, and that tells you that this expression, which is the partial derivative of u with respect to t, is equal to that other fellow which we did earlier, which was here, sorry, this is d square u by dx square, and if you remember, our equation now is utt is equal to c square uxx, because we are trying to do the most general thing. So this fellow we have to multiply by c square. It's just a constant. We have to multiply by c square. And that's what we have done here. This is c square times the derivative with respect to x, and this is the derivative with respect to time. See, there are lots of cancellations now. Wonderful cancellations. This psi square terms, this goes. This second order derivatives in eta also goes. Only thing that remain are these mixed partial derivatives. Okay? When you group them on the other side, okay, you get this. Because c is just a fixed constant, so this is what you get. See, this is what I said. If u solves the wave equation in the xt variables, and you make this particular change of coordinates, where xt is taken to psi eta, where psi eta are x minus ct and x plus ct. Okay? In these new variables, your v, which is essentially the copy of u, is satisfying this. Okay? This is easy to integrate. Okay? Now, both are equivalent. If v solves this, then u solves the wave equation in the xt plane. Now, let me just support my claim that this is easy to integrate. So you have got this, which implies what? I can rewrite this as d by d psi of dv by d eta equals to 0. So I am claiming that there is some function when differentiated in the psi variable is 0. So it should be constant with respect to psi. Okay? So it can be any function of eta, for example. So that's why we have dv by eta is g of eta. We don't know what it is, okay, some arbitrary function. Now, if you integrate this now in the eta variable, because this is a differential equation in the eta variable, this has got a primitive. Okay, this is some function you want to integrate, and you call that primitive as q. So this v of psi comma eta now is the primitive of this, which we are giving a name q of eta, plus some constant, and that constant can be any function of psi also. So you call that fellow as p of psi. Okay, where q is the primitive of g. Okay, so far this q and p are just notations. We don't know what they are. Okay, so the only thing that is important is any general solution to this equation. This is what we have just done in these two lines. If you are looking for a solution to this equation, d square v by d eta d psi is equal to 0, a general solution to this equation, thanks to this little computation here, should look like this. Some function of eta alone plus some function of psi alone. That is the observation we make here. Okay? Any solution to this problem should have this structure. We just don't know what that q and p are. We will find out, because we have still not used the initial data which is given to us, u0 and u1. Okay? So that p is just a function of psi. Okay, so recall that u of xt is this. Now, v of psi comma eta, that was just a name for u of x comma t. So we are just u of x comma t is equal to, what was psi? X minus ct. And what was q? X plus ct. Okay? So, in terms of the original xt variables, we have shown that the solution to the wave equation should have this particular structure. Okay? And in the very first observations we did in the morning's lecture, there was something similar to this. There the c was 1. That's why we were writing, you take any smooth function, you put the input as x minus t or x plus t. Those things are solutions to your wave equation, and that's what we are landed in. Okay? It turns out that any general solution to the wave equation should have this form. Okay. Now, the only drawback so far is that p and q are undetermined. We don't know what p and q are, and we will try to use the data to figure that out. We will figure out what p and q are. Okay? I hope you are with me on this. Huh? Okay. Okay. So let's use the first data. U of x comma 0 is u0 of x. Okay? We have just shown this thing, right? U of x comma t, let me take my luck with this. So you got u of x comma t is some p of x minus ct plus q of x plus ct. This is the most general solution that we have for the solution to the wave equation. And in this relation now, let us blindly take t is equal to 0. Okay? When I take t is equal to 0 here, I get u of x comma 0, and that has got a name. It's got u naught of x, which is given. And this becomes p of x, this becomes q of x. Okay? So that's what we'll do. So u naught of x is just the sum of these two functions. So you are trying to find two functions p and q such that their sum is your initial condition u naught. Okay? And now we will differentiate this and use the other information that is given. Okay? So let's differentiate this fellow with respect to time. Okay? When you differentiate this with respect to time, you get p prime evaluated at this point times minus c plus q prime evaluated at this point times plus c. So that's what we have written here. And what is given to us? Ut at x comma 0. So you blindly take t is equal to 0 in that expression and equate that to, okay, this fellow is u1 of x. Okay? So u1 of x is simply minus c times p prime plus c times q prime. Okay? You are looking for two functions p and q such that their sum at every point in R equals to your given function u naught, and the sum of their derivatives with that coefficients minus c and plus c should be equal to that other given function u1. So now we have to use these two information, this and this, to find those functions p and q. Okay? That's what we will do. Whenever you see derivatives, you try to integrate. Okay, that's what is done here. So you got this relation, you integrate from 0 to x. Okay? When you do that, this left hand side is just integration of u1, and on the right hand side, we are now going to use fundamental theorem of calculus, which says that when I differentiate p prime, and when I integrate p prime, I get p at one endpoint minus the p at the other endpoint, and that is here. The two endpoints being x and 0. And when I integrate q prime, I get this. Okay, with the coefficient c. We have simply integrated and we have got so far. Okay? So, now we have got this relation which involves p and q, no derivatives. And there is one more relation which involves only p and q, no derivatives. Okay? There is an integral of u1. So, there are two relations which are valid at every point x. These are the two relations which we have. Using these two relations, is it possible to find this p and q is the question. Okay? Now, first and foremost thing, what have we done here? You see, there's p of x here, there's minus p of x here. So we can blindly add these two equalities. That will give you an expression for q of x. This is the expression that you get. But there is this annoying q naught and p naught which are still there, but somehow luck is on our side because D'Alembert has got a famous name, so this should work. Okay? So now, when you sum them, the p went away, now you subtract them. Okay? So that the q goes away, and now you will get an expression for p. Okay? So you get this. Okay? Now you have got these relations. And you please note that these two have got opposite signs now. So when you sum them, it will be fine. Okay? So, you are not summing, I'm sorry about that. You got an expression for q and p, and you have got this other relation. Whenever you have got an expression for p and q, you are done. Okay? And u of x comma t is just p evaluated at x minus ct and q evaluated at x plus ct, both being summed. Okay? And when you sum these two relations, these two things are cancelling each other. So the remnant of q of 0, p of 0, they are gone. Okay? So what you will be left with is these two terms being evaluated at x minus ct and x plus ct. Okay? Once we share these slides, I want you to actually look at this slide and appreciate the way everything falls in place. Okay? Just D'Alembert's wonderful idea was to make that particular change of variable, which took xt to psi a term. And then it's a bunch of tricks which any BSc first year student can do. Okay, so you get this here, you have got an expression for p and q, you plug it here. evaluated at x minus ct and x plus ct. Okay? And when you do that and sum both of them, it's very important that you are summing here so that these two terms go away. First you get this. Okay, the terms involving u naught of x. You see, this q should be evaluated at x plus ct and p is evaluated at x minus ct, and you are summing them. So there is a 1/2 next to them. So you are essentially averaging the value of u naught at 2 points. Now here p is evaluated at x minus ct and q is evaluated at x plus ct, and you are summing them. Okay, and I think I have explained the details here. So you get it here. Okay, now see, in both of these things you are integrating the same function u1. In one you are going from 0 to x plus ct, and in the other you are going from 0 to x minus ct. So this is essentially, and you are subtracting this off. So this fellow is essentially integration from x minus ct to x plus ct. Okay, this is just the property of the definite integrals. So you get that. So see, this is, and we were after a recipe to write down the solution to u, right? If you are given u naught and u1, how do you write down the expression for u? And D'Alembert succeeded in this. He just says, okay, if you are given the wave equation, utt is equal to c square uxx, okay, and you are given this data, u of x comma 0 is u naught of x, and ut at x comma 0 is u1 of x. So this is the standard initial value problem. Then D'Alembert says, okay, u of x comma t is simply, you take the average of the values of u naught at 2 points, u naught of x minus ct, u naught of x plus ct. This is the first term. Then there is an integral term, 1/2 of integration from x minus ct to x plus ct of u1 of s ds. That's it. So once you are given u naught and u1, you can blindly write down this expression, and that fellow is a function of x and t variables, and it turns out to solve the wave equation. Okay. So this is the wonderful formula which goes under the name of D'Alembert. Okay, this is known as the D'Alembert's formula for the solution to the wave equation on the real line. Okay, where x runs in R. So the one takeaway from this is, you see, if I am interested in the value of my solution to the wave equation at the point xt, I need to know the value of u naught only at 2 points, x minus ct and x plus ct. Everywhere other than these 2 points, what is the behavior of u naught, it doesn't matter for the value of u at xt. Only the value of u naught at these 2 points matter, and the value of u1 in this interval matters, x minus ct to x plus ct. Outside that interval, the behavior of u naught and u1 is irrelevant for the value of u at the point xt. Okay, so this is a very important observation to make. Okay, I have some pictures to show later on. So the values of u naught, so the value of the solution at the point xt depends only on the values of u naught at these 2 points and the values of u1 in this interval. Okay, somehow this fellow, no, the guy is here, even in that triangle picture, that x minus t, x plus t was coming into picture. So these are all related, and if you remember the first order, the transport equation that we did, it turns out that inside the wave equation there is a transport equation sitting. That's why this behavior is happening. Okay? Okay. Actually there are 2 transport equations sitting inside the wave equation, for whom one characteristic is x minus ct and the other is x plus ct. So these 2 are happening. But ignore what I just said. Okay, we are just trying to understand from calculus, and we will just stay with this. Okay, so now let's try to understand this D'Alembert's formula. This is a formula. Okay, this is just a recipe. Somebody gives you u naught and u1, you blindly write down this formula, and if you are convinced by the calculations we did, it solves the wave equation with that data. Okay, and this morning we convinced ourselves that there cannot be 2 solutions. So this is the solution. So we need not look for anybody else. So this is the D'Alembert solution. Okay, you take any point xt, you just do this, and this is the picture. So if I am standing at this point, x naught t naught, and I want to know the value of my solution u to the wave equation at this point, I have to only worry about this interval. The behavior of my data outside this interval is irrelevant for the value of u at this point. Okay, as long as the wave equation is concerned, because the u naught is evaluated at these 2 points and u1 is integrated in this interval only. Okay, so outside that interval, the behaviors of u naught and u1 is not relevant for u. Similarly, and this here you encounter this notion of domain of dependence. Okay, by domain of dependence, as the name suggests, if you're standing at a point on which part of your initial axis your solution depends on, the domain on which your solution depends on at that point. And D'Alembert's formula essentially tells you that this is that interval. This interval x minus ct to x plus ct is the domain of dependence of your solution at the point x comma t. We are just giving a name. So, but it's a very important notion to have. See, we are just studying the one-dimensional wave equation. There are wave equations in higher dimensions also, where x runs in R2 or x runs in R3. Life becomes a bit tricky when you go to higher dimension with the wave equation, and there the notion of domain of dependence becomes very important. Okay? In 1D, it looks very simplistic in the sense that, okay, it's just an interval, why care? Okay, but in higher dimension, this has value. But for now, okay, we will take baby steps. We will do this thing. Okay, so this domain on the initial axis where the solution at the point x comma t depends on, that is known as the domain of dependence, and it's actually given by an interval, explicit interval, x minus ct to x plus ct. Okay. Okay. Now there is also domain of influence. Now, it can be deduced again by the domain of dependence computations of the D'Alembert's thing only. Now, see, we know that if I am standing at this level capital T, let's say, this is the T axis, okay? Now, we know that if I stand at this point, this is x naught minus ct, there is the triangle picture, right? There is one line which is going with slope c, and there is one line which is going with slope minus c. Okay? So this fellow, this point is always influenced by the guys coming from this interval, right? So if I'm standing here, again I will draw a line of slope minus c and slope plus c. So for a guy who is sitting here, this will never be influenced by this point, because the slope of the line of slope minus c would never hit this point. Okay, so the guy standing here is never influenced by this point. So the point I'm trying to make is, only for those points standing on this red line here, when you draw those lines of slope plus c and minus c, this point will be part of the interval of the domain of dependence. Once you go out of this red line, you draw those two lines, one with slope c and minus c, this point x naught is never part of that interval, is never part of the domain of dependence. So this red line is referred to as the domain of influence, in the sense that the value of your initial data at this point can only influence the value of your solution for those points sitting on this red line, and nowhere beyond this. Like for the guy at level t is equal to capital T, because if I draw this line at the time t is equal to capital T, beyond this, the points along that line are never influenced by the initial data here. Similarly, along that line, beyond this point, nobody else will be influenced by this point. Okay? Because from the previous picture, you know what is the domain of dependence. Okay? Because the point here is, the solution at this point is influenced by this triangle, this thing, the base of that triangle. This is of slope c, this is of slope minus c. That is the most important thing. Okay? So at any point you stand, you have to draw those two lines, one with slope c and one with slope minus c. When it hits the x-axis, you will get an interval, and that is the interval which is influencing your values at that point. Now, going by that logic, if I draw this line at the time level capital T, this is the only patch of those points which are influenced by the values at this point. So this point can only influence at the level T is equal to capital T a bunch of points, which is the red line, and that is known as the domain of influence. And it can keep going like this. You see, this is the line of slope C, this is the line of slope minus C. It can keep going, and when you talk to people who do hyperbolic equations, they talk about light cone and all these things. In R2, your cone is a triangle. Okay, it's just this. So if you are the data U0 or U1 and you have some values at this point x0, your values can influence only those guys who sit in this thing, who come in this region. Outside that thing, your influence is not felt. Okay, so that's why it's called domain of influence, and that can be easily read off by that formula, D'Alembert formula. Okay, so these are some standard terminologies people use: domain of dependence, domain of influence, and this is what they mean. Okay, every wave equation has got a speed, and that C is known as the speed of the wave equation, and that decides the slope of those lines that you are considering in the triangles. Okay, domain of influence. I hope this is clear. Okay, and this is the most important property of the wave equation. This is known as the finite speed of propagation, and we use this while proving that energy conservation property. It essentially means the following: you have got an evolution equation because there's this time variable. Okay, you can think of it, the evolution is happening with time. If you start with an initial data which is compactly supported, your solution also stays compactly supported. That we claimed. And that is true with this wave equation. This is seriously not true with the heat equation, because in heat equations, if you give a solution with a very small compact support, your solution will be not having any kind of compact support as soon as you depart from T. Tomorrow I'll give an example to that effect. Okay, but now this is the finite speed of propagation. This phrase is for essentially claiming this fact that your U0 and U1 are functions of the x variable. Okay, and we told that it's those two are compactly supported. That means there is some closed interval of finite length beyond which the U0 and U1 are just zeros. Okay, so there any non-trivial behavior is happening in that closed interval. Now, your U, which is a solution of the wave equation, is a function of x and t variables. Suppose I fix t, say t is equal to 1. Okay, when I fix t, it just becomes a function of the x variable. The claim here is that u of x comma 1 is also a compactly supported function in the x variable. The compact support need not be the same compact support as your U0 and U1. It can be a bit larger, but you can still find a closed interval outside of which your u of x comma 1 is 0. Okay, in the x variable. So that happens for any t that you fix. You can fix t to be 1,000,000. There will be a closed interval outside of which your function is essentially 0. So that's what it means for an equation to have finite speed of propagation. That means you are giving certain information at the initial stage, and that information is being propagated at a finite speed. It does not go at an infinite speed. Okay, unfortunately that is what happens with the heat equation. Even if you give some data in an interval like minus epsilon epsilon, where epsilon could be 0.1, your solution will feel that effect forever. Okay, the heat equation has that drawback, in fact, and we'll see that. And finite speed of propagation is essentially this. It's again those minus c plus c lines. See? Suppose this is the interval a comma b where both u0 and u1 are supported. Okay? Now, you go to that. At each of those points, you draw those cones. Domain of influence. Like, what does a point here influence? It can influence at most that cone, right, from the previous slide. So, in order to find a patch of that line at level capital T, you have to essentially draw a line of slope minus c at the left end point and a line of slope plus c at the right end point. So this is the patch that is influenced at capital T level. beyond which, at the level of capital T, you are not feeling the effect of the initial data. You will be 0 for all those points x beyond less than a minus c capital T and greater than b plus c capital T. Okay? At that level, time capital T. So it's all about, as I told you, you have to fix a time and then look at it as a function of the x variable. It will be compactly supported. Okay? As you can see, the support is increasing. See, this is the compact support of your initial data, AB. And at level capital T, it has grown by a little bit. Okay? In fact, exactly by 2 times CT amount. Here it has gone by CT. Here it has gone by minus CT. So you exactly grow by 2 times CT. But the most important point is, at every level T, you have got a compact support for your function. Okay? So this is known as finite speed of propagation. Okay, compact support of the solution. It is time dependent, but at every time T, the support is compact. Okay, so with this I will end today's lecture. Don't worry about the number of slides, we will take it up tomorrow. Okay, so when we started, we showed that there is this energy which is conserved. Like if you take the solution to the wave equation, you take the corresponding E of t, which is essentially the square of ut and the square of ux integrated in the x variable. This function of time is just a constant function and it's equal to E of 0. This is what we proved. But E of t has 2 parts in it. There is potential energy and there is kinetic energy. There is a wonderful property of the wave equation, which was, I think this discovery goes back to Einstein. Okay, it's known as equipartition of energy. It says if you wait long enough, that P of t, which is the potential energy, and the kinetic energy K of t, they become equal to each other. Okay, all along you are keeping this E of t is equal to E of 0, but somehow they are balancing each other out in the last time. Okay, and this can be actually proved by the D'Alembert formula we have just derived. So this is the statement of the equipartition of energy. It says, okay, you take 2 smooth functions with compact support, u0 and u1. These are the data which are going to your wave equation, and you are taking this initial value problem. utt is equal to uxx, ux0 is u0, utx0 is u1. Okay, this is our standard setting for the wave equation. And let k of t and p of t be their potential, kinetic and potential energies that we introduced earlier. The claim is k of t actually equals to becomes equals to p of t for large enough t. Okay, after some time these 2 things start becoming equal to each other. Okay, that means your total energy will be partitioned equally. Okay, one half will be kinetic energy, another half will be potential energy, because we know that the total energy is conserved. It is not changing with time. So you may start off with a setting where your kinetic energy is larger than the potential energy, but your wave equation makes sure that they are equally partitioned with time. Okay, and this wonderful property can be proved just by that simple formula of D'Alembert. Okay. Don't worry about the second part, because I copy pasted this from one of the slides which had one more part in the assertion. So I'll change that also. This is just a consequence of the D'Alembert's formula. So let's start with the D'Alembert's formula. Okay, this is D'Alembert's formula, right? Here C is equal to 1. We have taken just C is equal to 1 and we just wrote down the D'Alembert's formula. What are we supposed to show? We are supposed to show that integral of ut square is equal to integral of ux square for large t. Okay, where the integration is happening in the x variable. So let's compute what is ut from this formula. Let's compute the derivative with respect to time. Okay, now we have all become experts in this. Given any function evaluated x minus t, okay, so this is that. When I differentiate this, I get u0 prime evaluated x plus t. And this fellow, you see, this integrand has no explicit dependence on t. So, and here we have just used that Leibniz integral rule. We get this. I ask you to just check this computation. Okay, it will come. So you get this. Now let's compute the spatial derivative of this guy. Okay, you get this. So you have got an expression for ut, you have got an expression for ux. we are supposed to compute this fellow. We are supposed to show that integral of ut square dx over r is actually equal to integral of ux square dx over r for large enough t, because one of them is potential energy, one of them is kinetic energy. So those two are equal to each other. We have got an expression for each one of them, and we have to simply square them, okay, and integrate. And for that, we use this algebraic identity which we all study. A square minus b square is a plus b into a minus b. So that's all we have used here. Okay. So there is a square minus b square. So there is a plus b into a minus b. You got an expression for a and b. You simply add them, subtract them. There are lots of cancellations happening. So you will be able to get an expression for this guy in terms of this product, and then you simply integrate in the x variable. Okay, and show that it becomes 0 for last time t. So now let us compute the sum of these two expressions. Observe carefully what happens when you sum. There is u1 of x minus t, there is negative of u1 of x minus t, and this u1 of x plus t is there, that will stay on. And here there is one more cancellation happening. This u0 prime, u0 prime. And when you subtract them, the guys who did not cancel, they cancel. Okay, so that's what happens. So you get this. When you sum them, you get these terms. When you subtract them, you get these terms. The main thing here is that both of them, this fellow is evaluated at x plus t. This fellow is evaluated at x minus t, both the terms. Okay? Now you simply, you have to multiply them, right? Because this times this is this fellow. A square minus b square is a plus b into a minus b. So now you have got two terms being added here, two terms being added, you are multiplying them, so you get four terms. So you get this. So this product, this product, this product, and this product. Now observe the thing here. In every product, you have got one term evaluated at x minus t, and another term evaluated at x plus t. That's the thing which makes the magic happen here. Because you know that you have assumed that u0 and u1 are compactly supported. So if I stand at a point x and I take t large enough, eventually my either x plus t or x minus t will go out of that compact set. Okay, and so that function will be 0. That's the whole point here. Okay. So it vanishes for large enough t. I hope this point is clear, because you see, suppose I stand at a point x. Okay, I'm fixing some point x, and I take t large enough. Okay, when I take t large enough, either x plus t will go out of that interval AB, or x minus t will go out of that interval AB. In either case, one of them will vanish, because both u1 and u0 are assumed to be compactly supported, so they will vanish and they will not contribute. Okay, so this is the point I was trying to make. So in particular, this is the exact amount of time that you have to go. Okay, if you go 1/2 of the distance of the length of that interval, you will make sure that either of them will go out, and each of these terms has either x plus t or x minus t evaluation in it, so that will, because it will vanish, you integrate, so you have actually shown that this is 0. For large enough t, this is 0. And one of them is phi of t, one of them is k of t. So this is a wonderful property called the equipartition of energy, because energy is being partitioned at large times. And you see there is, okay, this we will not get to. There is nothing spectacular here, it's just calculus, okay, and perseverance. So you will get, okay. Okay guys, I stop here in the interest of having some tea, okay. And also if you guys have any questions on the problem sheet that was given yesterday, and also the other things that we were discussed or anything here, feel free to ask. The rest of the things and something more which relates to what you have studied in the heat equation with regards to the Fourier series, because you can use Fourier series to find solutions to the wave equation also. Okay, and that we will do in tomorrow's lecture. Okay. Thank you.